Hello students, welcome to lecture 5 of S block group 2 elements. Our topic is chemical properties. The alkaline earth metals are less reactive than the alkali metals. So these are the less reactive when we compare with the first group elements. And the reactivity increases on going down the group. So if you take that second group, beryllium to barium, if you go down in the group, the reactivity increases. In chemical properties, the first one, reactivity towards air and water. So the beryllium and magnesium are kinetically inert to oxygen and water because of formation of oxide film. Oxide film on their surface. So beryllium, magnesium are kinetically inert to oxygen and water because the formation of oxide film on the surface. But the powdered beryllium bonds in air to give beryllium oxide and beryllium nitride Be3N2, and magnesium is more electropositive metal, so it bonds in air to form magnesium oxide and magnesium nitride Mg3N2. In air, nitrogen and oxygen percentage is more, so the magnesium react with oxygen to give magnesium oxide and magnesium react with nitrogen to give magnesium nitride. And calcium, strontium, barium are rapidly bonds in air to form oxide and nitrides. And they can also react with water to form hydroxides. And next, second one, reactivity towards halogens. All alkaline earth metals, means second group metals, react with halogens to form halides. Let me take reaction. M is the metal and it react with halogen, the common formula X2. So then it can give metal halide MX2. So here X nothing but fluorine, chlorine, bromine and iodine. M is the metal, so that is beryllium, magnesium, calcium, strontium, barium. And the halide of BeF2, beryllium fluoride, prepared by the thermal decomposition of complex compound of NH4 taken 2 times and BeF4. So it is a ammonium tetrafluoroberylate 2. Its oxidation number is 2. So its name is ammonium tetrafluoro, 4 fluorines, tetrafluoroberylate and 2. Oxidation number is 2. The halide of BeF2 is prepared by the thermal decomposition of complex compound of ammonium tetrafluoroberylate 2 and the metal halide of BeCl2, beryllium chloride is prepared from the oxide of beryllium, BeO, beryllium oxide. It reacts with carbon and Cl2, and it is a reversible reaction. The temperature is 600 to 800 Kelvin. So at this temperature, the beryllium oxide react with carbon and chlorine, then it will give beryllium halide, means beryllium chloride plus carbon monoxide. Next, reactivity towards hydrogen. All the alkaline earth metals react with H2. On heating, it can form hydrides. Except beryllium. All the alkaline earth metals react with H2 to form hydrides except beryllium. Let me take that reaction. Metal M plus towards hydrogen H2 gives rise to MH2. So it is a metal hydride. So M means it may be beryllium, magnesium, or calcium, or strontium, or barium. However, we can also get that beryllium hydride by the reaction between beryllium chloride and lithium aluminium hydride. So that beryllium chloride react with lithium aluminium hydride to form beryllium hydride plus lithium chloride plus aluminium chloride, and balance that equation. So here 2 and here also 2. So that beryllium will not form that beryllium hydride when it react with hydrogen. But here we can get that beryllium hydride by the reaction between beryllium chloride and lithium aluminium hydride. Next, fourth one, reactivity towards acids. So the alkaline earth metals readily react with acids, then they can give H2 gas. So let me take the reaction. M plus HCl. M is the metal. The metal, it may be beryllium, magnesium, calcium, strontium, barium, gives rise to MCl2 plus H2 gas. Next, fifth one, reducing nature. Like alkali metals, means first group metals, the alkaline earth metals, means second group metals, are also strong reducing agents due to having large negative reduction potential values. So these alkaline earth metals are strong reducing agents due to having large negative reduction potential values, and alkaline earth metals reducing power is less than those of corresponding alkaline metals. So that second group metals having less reducing power than corresponding first group metals, and beryllium has less value. This beryllium having less reduction potential value compared to other alkaline earth metals due to large hydration energy. Next, fifth one, dissolve in liquid ammonia. Like alkali metals, the alkaline earth metals also dissolve in liquid ammonia to give deep blue color solution. Deep blue color. solution. This is due to ammoniated ion. So we know that there is a beaker. In that beaker we have ammonia solution, NH3. To that solution, if you add the metal, second group metal, so that metal give metal ion. So in that solution, the metal will give metal ion M+2 plus it lost 2 electrons. Means in that solution we have M+2 ions and electrons. So here, so in this solution we have metal and ammonia molecules. So here X plus Y moles of ammonia molecules and gives rise to, so here that metal ion surrounded by ammonia molecules, X moles of ammonia molecules. So here NH3, here M and NH3, X moles of NH3 and here +2. So it is called ammoniated ion. And plus there are electrons in the solution, so that electrons also surrounded by ammonia molecules. So here Y moles of ammonia molecules and here negative charge. So this is called ammoniated electron and it is called ammoniated ion. So due to this ammoniated ion, the solution will get deep blue color. Next one, general characteristics of compounds of alkaline earth metals. So the alkaline earth metals having di-positive oxidation state M+2 because it lost 2 electrons to get stability. And alkaline earth metals can form ionic compounds. Ionic compounds, but less ionic than the corresponding alkali metals due to increased nuclear charge and small size. More nuclear charge and small size. And beryllium, magnesium, oxides and other compounds are more covalent than the compounds of calcium, strontium, barium. In general characteristics, the first one, oxides and hydroxides. So the alkaline earth metals bond in oxygen to form monoxide, MO. M is the metal. So alkaline earth metals bond in oxygen to form monoxide, the formula MO, except beryllium. So the beryllium monoxide will not form. If the beryllium bond in oxygen, it will not form beryllium monoxide. And beryllium monoxide is covalent in nature. It is a covalent compound. And beryllium oxide is amphoteric in nature. It is a amphoteric. And other metal oxides are ionic in nature. Other second group of metal oxides are ionic in nature. and that other metal oxides are basic. So here beryllium monoxide is a covalent and it is a amphoteric, means it having acidic character and basic character. And except beryllium, the other metals are ionic in nature and they are basic. And oxides react with water to form hydroxides. Metal oxide react with water to form metal hydroxides. MOH taken 2 times. So it is a hydroxide. And with increase in atomic number, the solubility and stability and basic character increases. So here if you go from beryllium to barium, the atomic size increases. So due to increase that atomic size, the solubility and the stability and the basic character increases. And the basicity increases from magnesium hydroxide to barium hydroxide. And alkaline earth metal hydroxides, means second group hydroxides, are less basic and less stable than alkali metal hydroxides, means first group metal hydroxides. And beryllium hydroxide is amphoteric in nature and it reacts with both acid and base. So let me take that reactions. Beryllium hydroxide react with base. Base means it will give OH minus ions. So then it will form tetrahydroxyberylate. Beryllium OH taken 4 times and -2. So here the beryllium oxidation state is +2. So it is called tetrahydroxyberylate 2. And that beryllium hydroxide also react with acid. BeOH taken 2 times plus H2SO4 gives rise to BeSO4 plus 2H2O. And let me take another reaction. BeOH taken 2 times plus acid. Here I am taking HCl plus H2O gives rise to BeH2O taken 4 times and Cl2. So it is called tetra aqua beryllium 2 chloride. So here beryllium oxidation state is +2. So tetra aqua beryllium 2 chloride. And balance that equation. So here I am taking 2 and here also 2. Then in this reaction we have to take here 2. Now it is the balanced equation. So it is already balanced equation. So here that beryllium hydroxide, so it is a amphoteric in nature. It react with base and as well as it react with acid. So it react with base. So here it will give tetrahydroxo beryllium 2. and that beryllium hydroxide react with H2SO4, it will give beryllium sulfate plus H2O, and if it react with HCl, then it will give tetra aqua beryllium 2 chloride. So this is about oxides and hydroxides. Next one, halides. Except BeX2 means beryllium halide, all other halides of alkaline earth metals are ionic in nature. Ionic, but it is a covalent. Only that BeX2 is the covalent, and the remaining all metal halides are ionic. That beryllium halides are soluble in organic solvents because that beryllium halides are covalent, and the remaining halides are ionic in nature, so they can soluble in water, but they cannot soluble in organic solvents. And that beryllium chloride BeCl2 as a chain structure in solid state. So let me take that structure. Here beryllium chloride, and here also I am taking beryllium chloride, and here also I am taking beryllium chloride. So beryllium of one molecule connected to the chlorine of other molecule means that chlorine can donate the electron pair to the beryllium, and it can form coordinate covalent bond. And here also coordinate covalent bond, and here also coordinate covalent bond, and this one also, and here also we have another molecule. If you have another molecule, so it can also connect it to the beryllium, and here also if you have another molecule, we have to take here Cl. So it is a polymer. So BeCl2 has a chain structure in solid state. So it is like a chain, and the tendency to form a halide hydrates decreases if you go from top to bottom in the group. Means if you go from beryllium to barium, the tendency to form halide hydrates decreases. So let me take some halide hydrates compounds. With magnesium, MgCl2 8H2O, and with calcium, CaCl2 6H2O, and with strontium, SrCl2 6H2O, and with barium, BaCl2 2H2O. So here with magnesium, the halide contain 8 water molecules. The calcium chloride contains 6 water molecules, and strontium chloride contains 6 water molecules, and barium chloride contains only 2 water molecules. So here if you go from top to bottom, the tendency to form halide hydrates decreases, and the fluorides are less soluble than chlorides. Fluorides are less soluble than chlorides due to high lattice enthalpy. So this is about halides. Next, third one, salts of oxo acids. The alkaline earth metals also form salts with the oxo acids. Let me take carbonates of oxo acids. Carbonates. Already we discussed about that oxo acids. Let me take carbonates. Carbonates of alkaline earth metals are soluble in water. Soluble in water. And they can precipitated by addition of sodium or ammonium carbonate solution. So if you add sodium carbonate solution or ammonium carbonate solution, the carbonates of alkaline earth metals are precipitate. And the solubility of carbonates in water decreases as the atomic number increases. So if you go from beryllium to barium, the atomic number increases. Due to the increase in atomic number, the solubility of carbonates in water decreases. So here the solubility of carbonates decreases, and all carbonates decompose on heating to give carbon dioxide and oxide. So the carbonates on heating will give carbon dioxide and oxide. And beryllium carbonate is unstable and it can be kept only in carbon dioxide atmosphere. And carbonate's stability increases with increase in cation size. So if you go from beryllium plus 2 to barium plus 2, the cation size increases. So here the carbonate's stability increases with increase in cation size. Next, oxo acids, sulfates. Sulfates of alkaline earth metals are white solids. So they are white solids. And beryllium sulfate and magnesium sulfate are readily soluble in water because greater hydration enthalpy. Greater hydration enthalpy. And the solubility decreases from calcium sulfate to barium sulfate. So the solubility decreases from calcium sulfate to barium sulfate. And next one, nitrates. So all these are the oxo acids, carbonates, sulfates and nitrates. The nitrates are formed by dissolution of carbonates in dilute nitric acid. So the carbonates are dissolved in nitric acid, MCO3. So these are the metal carbonates. That metal carbonates dissolve in dilute nitric acid, HNO3. Dilute HNO3. Then it can give nitrate, MnO3 taken 2 times. It is a metal nitrate, and plus carbon dioxide plus H2O. So this is the nitrate. So the nitrates are formed by dissolution of carbonates in dilute nitric acid, and magnesium nitrate crystallizes with 6 water molecules, MgNO3 taken 2 times. It crystallizes with 6 water molecules, MgNO3 taken 2 times, 6H2O. And barium nitrate crystallizes as anhydrous salt, anhydrous. Barium nitrate crystallizes as anhydrous salt, and with increase in size decrease the tendency to form hydrates, and all nitrates decompose on heating to give oxides. So let me take a general nitrate formula. MnO3 taken 2 times gives rise to metal oxides plus NO2 plus O2. So here 2 and here 4. 2 into 2, 4. So let me take here 4. So it is a balanced equation. And here M is the beryllium, magnesium, calcium, strontium, barium. So all nitrates decompose on heating to give oxides, metal oxides. For example, if you take magnesium nitrate here, it will give magnesium oxide. If you take calcium nitrate, it will give calcium oxide. So this is about salts of oxo acids. Next one, anomalous behavior of beryllium. So that beryllium shows anomalous behavior as compared to remaining alkaline earth metals. Means the beryllium having different properties when we are compared with the other remaining metals which are belongs to same group. So that beryllium has anomalous behavior as compared to remaining alkaline earth metals, means second group metals. And beryllium has small atomic and ionic size. Due to this small atomic and ionic size, it can form covalent compounds. It can form covalent compounds. And ionic nature increases in the group from magnesium to barium. So that beryllium can form covalent compounds, and the ionic nature increases from magnesium to barium. Means the barium having more ionic nature than the magnesium. And beryllium does not exhibit coordination number more than 4 because it contains only 4 vacant orbitals. So if you take that beryllium, its atomic number is 4 and electronic configuration 1s2, 2s2 and 2p0. This is the outer shell. So in that outer shell we have 2s orbital and 2p orbital. So that beryllium having only 4 empty orbitals. So it can exhibit only up to 4 coordination number. So that beryllium does not exhibit coordination number more than 4. So these empty orbitals receive the electrons from the ligands. So that beryllium can form BeL4, means beryllium does not exhibit coordination number more than 4, and except beryllium, remaining alkaline earth metals exhibit coordination number 6, because the remaining metals having d orbital. For example, I am taking magnesium atomic number 12 and electronic configuration 1s2, 2s2, 2p6, 3s2, 3p0, 3d0. So in outer orbit we have 3s, 3p and 3d. So in 3s 2 electrons, in 3p empty orbital, and 3d empty orbitals. So we have more than 4 empty orbitals, and the remaining metals also having more than 4 empty orbitals. Except beryllium, remaining alkaline earth metals exhibit coordination number 6. So these empty orbitals receive the electron pairs from the ligands, and beryllium oxide and beryllium hydroxide are amphoteric. But the remaining alkaline earth metals are not amphoteric. Remaining alkaline earth metals are not amphoteric. Only the first element oxides and hydroxides are amphoteric in nature, unlike remaining alkaline earth metals. Next one, diagonal relationship between the beryllium and aluminium. Diagonal relationship means similarities between the first element of the first group and second element of the next group, called diagonal relationship. So here the ionic radius of beryllium plus 2 is nearly same as that aluminium plus 3. So beryllium has same properties with the aluminium. So here I am taking the first group, I am taking the second group as a first group. First element is beryllium, means in second group the first element is beryllium, and next group is third group. In that third group we have boron, aluminium, gallium, indium and thallium. So here I am taking second group as a first and third group as a next. So first element of the first group and second element of the next group. Next group means third group. So the first element of the first group and second element of the next group having same properties. So it is called diagonal relationship. So beryllium and aluminium having diagonal relationship, having same properties. So this relationship is called diagonal relationship. So in second group we have beryllium and magnesium, calcium, strontium, barium, radium, like that. In third group boron, aluminium, gallium, indium, thallium, like that. So here if I take magnesium as a first element in this group, and next group is third group, and the second element is gallium. So these two are having same properties, and aluminium, beryllium both are not readily react with acids because the presence of oxide film on the surface, and beryllium hydroxide dissolve in excess of alkali, means excess of base, to give berylate ion. BeOH taken 4 times and -2. Aluminium hydroxide also AlOH taken 3 times also give aluminate ion. AlOH taken 4 times and -1. So the beryllium hydroxide dissolve in excess of alkali to give berylate ion, and the aluminium hydroxide also gives the aluminate ion. And chlorides of both beryllium and aluminium have bridged chloride structure in vapor phase. Both chlorides having bridged chloride structure. Bridged chloride structure in vapor phase. And both the chlorides are soluble in organic solvents. Soluble in organic solvents. And they are strong Lewis acids. Strong Lewis acids. Aluminium chloride also having bridged structure. So here AlCl3. So 3 chlorines. And I'm taking another molecule, Al, 3 chlorines. So aluminum of one molecule connected to chloride of another molecule, means this chlorine can donate the electron pair to the aluminum of other molecule, and here also this chlorine can donate the electrons to the aluminum of other molecule, and they can form coordinate covalent bonds. So these chlorides are called bridged chlorides. The aluminum chlorides having bridged chloride structure, same as that beryllium chloride. Beryllium chloride also having bridged chlorides. See here, the beryllium also having bridged chlorides as that aluminum chlorides. And Be plus 2, Al plus 3. Both ions have strong tendency to form complexes. The complex of beryllium, Be, F taken 4 times and -2. The complex of aluminium, AlF6 -3. So Be plus 2 and Al plus 3. Both ions have strong tendency to form complexes. So this is about diagonal relationship between the beryllium and aluminium. Second group of beryllium and third group of aluminium having same properties. That relationship is called diagonal relationship.